Hello, I'm Chiara and I'll present our paper What Can a Cook in Italy Teach a Mechanic in India? Action Recognition Generalization over Scenarios and Locations. As humans, we understand the action cut to indicate splitting something into two parts. We can recognize a cook cutting a carrot with a knife, a mechanic cutting a cable with pliers, and a construction worker cutting metal with an angle grinder. We are able to generalize the action regardless of the scenario and the relevant tool. There are many more tools we use to cut across further scenarios. Cutting a paper with scissors during arts and crafts scenarios, cutting a hedge with shears whilst gardening. We can even cut with our hands, like this example of cutting from a pile of mud in construction. We propose this practical problem of generalizing the action across scenarios. This is a new problem, previously unexplored. We introduce the term scenario shift to define this domain gap and address it in this work. We combine the scenario shift with an exploration of where actions take place. We show 3 examples of cutting in the cooking scenario in Italy, India, and Rwanda. The environment and objects differ per location, showcasing rich cultural diversity. Generalizing across the location shift has been explored before. To study both scenario and location shifts, we introduce Argo1M, a new dataset from egocentric videos of the Ego4D dataset. We identify actions in 13 locations and 10 scenarios, and assign each video clip an action class out of 60, given the provided narrations from Ego4D. In total, Argo1M contains 1.1 million samples, which makes it the largest domain generalization dataset to date. To assess generalization across both scenarios and locations, we form our test splits as follows. Given Argo1M, we consider one scenario, for example cooking, and one location, for example Japan. We take their intersection as the test set. We exclude all samples from either cooking or Japan from the training set. In total, we curate 10 trained test splits to evaluate generalization over scenarios and locations. We first demonstrate action recognition models struggle to generalize over these test splits. We give an overview of our architecture. For each video in the batch, we consider both the video and its text narration. We use pre-extracted visual features and a clip model for text embedding, and learn 2 projection layers, F and G. The video embedding is then used to train a classification with standard cross-entropy loss to classify the action. We use the same projection layer for all the videos in the batch. Those are used for learn cross-instance reconstruction. This is done by learning a query and a key embedding for each video in the batch, and then computing the dot product between those. Self-masking is applied to avoid trivial solutions by using the video itself. The resulting weights are then used to reweight the video features. The reconstruction then replaces the visual representation of the video from others in the batch, excluding the video itself. We refer to this as a cross-instance reconstruction CIR, which is the name of our proposed method. The resulting reconstruction is then used for video text association. We jointly reconstruct all videos in the batch at the feature level, and use noise contrastive estimation of these reconstructed video text pairs, and importantly backpropagate this loss to the video features. Our main objective is to train the projection F, so it learns to generalize across scenarios and locations. We use a second cross-instance reconstruction obtained by standard cross-product attention. This is trained to recognize the clip's action class. This reconstruction solely focuses on the action class cut in this case, learning to generalize this action over scenarios and locations. Importantly, it's classified using shared weights with our main classifier H. At inference time, only visual information is used for classification. No reconstruction or batch-based knowledge is used. We visualize how reconstructions take place during training. The top 5 support set videos with the highest weights in the reconstruction to the query video are shown. For each query, the bar shows the score of the support video. CIR attends to samples belonging to other scenarios, other locations, and both. We show here results of the proposed CIR method with respect to the other popular domain generalization methods on 2 selected splits, and on the average over the 10 splits. We first compare with the empirical risk minimization baseline, that is cross-entropy without a generalization objective. We use 6 generalization baselines, all trained jointly with cross-entropy. The proposed CIR method outperforms all previous methods consistently. Please check our publicly released benchmark, code, and models. Thanks for watching. Visit us at the poster session.